Alright, in the last video, we had our linear circuit, we applied the Laplace transform, and we found the transformed circuit by using these S-domain models. So we got something like these. We are using here voltage sources to represent those initial conditions, the voltage and the current, but you can use also current sources if you want, and the model is going to be slightly different than this one, but also works. And now that we have our circuit in the Laplace domain, we're going to try to find the equation or extract the equation out of that circuit. And we're going to use a set of familiar tools or tools that you are familiar with in order to get that equation. Alright, so in the Laplace domain, the cool part is that we are still relying on this Ohm's law, where the voltage is still related with the current times that impedance, which makes everything pretty much linear and similar to a resistive circuit. So that means that all the tools that we used in the past to analyze a resistive circuit, such as Ohm's law, KCL, KVL, circuit reduction, source transformation, or equivalent impedance, not resistance in this case, they apply. And you can also combine these tools together, so you can use more complex techniques such as mesh, nodal, Thevenin and Norton, superposition. All these is valid to analyze and extract the current or voltage or impedance of interest. Alright, so for this particular one, we need to define what we want to find. Do we want to find current or the voltage? And let's just find the current that flows through this inductor. Alright, cool. So now step number one. The first thing that we're going to do is, still in the time domain, we're going to find those initial conditions because they need to feed into our S domain model. So we're looking at when t is less than 0 and things are stable, nothing is changing, and we call that DC. So if you recall the equations of a capacitor, or the equation of a capacitor, the current flowing through the capacitor is C dV C dt. So if at DC nothing is changing, this derivative is equal to 0. That means that there is no current flowing through the capacitor. Well, if there is no current flowing through this capacitor, I can go to this circuit and substitute that capacitor by an open circuit. And that's what you see over here. Well, if it's an open circuit, the voltage across the terminals of that capacitor is going to be equal to the voltage across this power supply, which is 4 volts, and that's your initial voltage. Now you apply similar thought process to your inductor. You know the equation for your inductor. At DC, nothing is changing, derivatives are 0. That means that the voltage drop across the inductor is 0. So if the voltage drop is 0, that means that I have a wire. Because remember, voltage is a differential of potential. So if it's 0, it means that this potential is the same as that one. Alright, so that happens when I have a short circuit or a wire. So the inductor behaves as that short circuit and becomes just a simple circuit like this. If I apply Ohm's law, so 20 volts divided by 10, you get an initial current of 2 amps. Alright. Now, step number 2, we're going to plug those initial conditions that we just found on the S model. So this is the S model that we have, and we just plug 2 and 4 on the respective positions here, and you get this S model. And this is the one that now we're going to use. On step number 3, you're going to pick a tool or a set of tools from the ones that we presented earlier, and you're going to try to find IL of S. Alright, so at this point I recommend you to stop the video and try by yourself. Just treat it again as a normal resistive circuit, where the resistance, or in our case in the S domain, our impedance, just have that S, and use whatever technique you want to use. So pause the video, take your time, and then check one way of solving these in a minute. Alright, so for my case, I'm going to just change the S model, and instead of using voltage sources here for the initial conditions, I'm going to use current sources. And that's just to show like potential mistakes or issues that can arise when you use this type of things or models. And I just want to highlight how you things that you need to be careful. So if I do that current source, or if I change the model, the S model, to current sources, notice here that now instead of having this voltage source in series with the inductor, I have that current source, and now it's 2 over S, it's that initial condition over S. And I apply the same thing for the capacitor, where I put the current source in parallel with the capacitor. All right, and it becomes 4 over 20. All right, one thing now that it's important to emphasize is when I change, or in my case, when I change my model to a current source, I need to be careful with the current that I'm trying to find. Notice now that my IL, when I go to my model with current sources, is no longer just the current that flows through the inductor. It's the current that flows through the inductor that I'm calling I, plus that current source. So I cannot forget this. This is a common mistake. We just call this IL, and then we forget to do this small addition at the end. All right, so having that in mind, and I'll get back to this later. Now, what I care is if I find IS, I can plug it here and get my IL of S. All right, cool. So I have my circuit, and I'm going to do, in this case, for now, a source transformation. So I'm going to pick up this voltage source and divide by 10. And if I do that, I get my current source over here. And still having in mind this, we don't need this for now. And the next thing that I'm going to do is to simplify that model. Notice that I can put the current sources together, where this one actually cancels out with that one. So I just get the 4 over 20, and I get all these impedances in parallel: the resistor, the inductor, and the capacitor. And I still have, it's important to keep track of the current that you want to find in this case. All right, so I still have my I of S over there. Now, the next tool that I'm going to use, I could use KCL over here because everything is in parallel, but I'm actually going to apply a current division at I of S. If you don't recall current division is simple as the current of interest is going to be equal to the total current times the equivalent impedance over the impedance that it's related with the current of interest. All right, so let's plug that here. So my I of S, which is my current of interest, is equal to my total current, which is 4 over 20, times my total impedance divided by the impedance of interest, in this case is 4S. All right, let's find the total impedance. In this case is 10 in parallel with 4S in parallel with 20S. So if you do all these, you get this equation. Now if I substitute these on my current, I get the following I of S. The problem is still not solved. I just found I of S. Remember that I of S is actually related with IL of S in this fashion. So I need to pick up this I of S and add to S, and I get my algebraic equation.